So, as I said, welcome to Fun in Syskill Part 1. All right. So this is where most of your bugs will come from for to be honest, for assignment 2 and assignment 3. By the way, for assignment 2, I will release it like sometime tomorrow, to be honest. You have 2 weeks to finish, and uh, it will be a little bit longer than assignment 1, but from what I've heard so far, it's a lot less painful because it's not in shell, it's in C. So like standard programming practices without having to worry too much about like white space or things like that will not apply. You have way more control over what you can do because you have if else, you have for loop, much easier. I mean, shell also have if else and for loop is a lot more restrictive. All right. All right. Recap. We covered data types, right? They have int, character, and float, right? And what they represent is the data type tell what is the type of the value supposed to be. For example, the value of 65 in character is letter A. To be more precise, the capital letter A. All right. But if I cast this character into an integer, it becomes 65. Inside your computer, it's still represented by the same binary, right? The same binary is 10000001, right? And that's 65. C only support basic data type except when you use array and struct and the combination of those things. Okay. We also have if else and switch case and for loop, while loop, do while loop, and also the break and the continue statement. So we covered this on the Tuesday lecture. All right. We also have printf and scanf, right? And today we will talk about what is that ampersand doing in the scanf. All right. And to be more precise, the ampersand is the operator. It's a unary operator. Unary means that it's an operator that takes in only one input. A binary operator like a plus takes two inputs like A plus B, right? Another sample of unary operator that can also take the binary form is the minus. The minus sign can be A minus B or negative A. Negative A takes one input and it knows that it's a negative value of that number. All right. Ampersand is a unary operator that tells the location of A. So A is a variable. Ampersand A will give you the location of A inside your memory. Okay, so that's dive into the concept of pointer, right? So the thing is, in any program, to be honest, I don't have to motivate using C, but think about it, right? When you write a program, you have to operate on the data, which means that it's going to be somewhere on your computer, right? Every piece of data, every piece of variable that a program uses is stored somewhere in DRAM. DRAM is that memory thing that when you buy a new computer, right? It will say, hey, what's the CPU that you want? You have like Intel, AMD, or like M1, M2, and potentially M3 coming soon, chip from Apple, right? So that's a CPU side. Then you have the memory. You say, hey, how many gigabytes of memory do you want? These are DRAM. These are used by the CPU. And the CPU uses this to store both the program and the data, right? So every piece of data you're using on your program stored there. And to know where they are, similar to how we live our life, right? What do we use the address for? To tell location, right? The same thing here. DRAM is big. How big is 16 gigabytes? 16 gigabytes can store a lot of integer because each integer is 4 bytes long, right? So if I have 16 gigabytes, I can store billions of integer. It means that each integer is supposed to have an address so I can know where they are. So that I don't have to go search the entire thing to find my data. I just know, okay, that's where I am. I go that location and I should be good. All right. These addresses, think of it as is the home for the data and it has certain address. In C, every variable has its own address. Basically, every variable has its own address. And the array, for example, will have the range of addresses because the array contains multiple items, right? Each item has its own addresses. So the array would cover this range of addresses. And hopefully, your program doesn't access anything outside of this range. Why is that a good thing? Well, it's not your data. If you, let's say this is your array, right? How many items are here? 5, right? So you can go to A of 0, A of 1, A of 2, up to A of 4, right? If I want to do like A of 10, which means go to like 11 items, this should not be valid, right? So basically, your program should not do that. Also in C, you can create the data type that not storing the value, but store the address. So I can create the data type that store an address. We call this a pointer. And as the name suggests, it doesn't store a value, it just points to somewhere. It points to a location. So in here, if I say in A equal 10, A is a variable and store the value of 10. I can write ampersand A. This would give me the address, basically the location of where this value 10 is. Technically, as we will learn in the last module, basically the last 2 lectures of this semester, this address is a virtual address, but we're not going to worry about it for now. Think of it as an address, all right? To visualize this, right? Let's say you have DRAM of n bytes. It can be like 4 gigabytes or whatever. And let's say there's a number 7 stored at address 100. I store an integer 7 at address 100. How big is an integer? 4 bytes long. All right. So this number 7 would take 4 bytes in size. If I want to store a next number 5, where is this address for the value 5? Should it be 101 or 104? 104. Each address corresponds to each individual byte. So the next number is going to be at 104. Again, store a 4 bytes integer. And you can keep doing this for the number that you use, for example, in an array. In this case, you have the array of size 3 that store the number 7, 5, 5. In total, the size of this array is 12 bytes. If you do size of this array, you get 12. All right. So to use the pointer, right? For example, you can first declare, right? You first declare by just typing this in star A. In star A, this will create a variable called A that has the pointer type. It's not an integer type anymore. It's a pointer type. And the purpose of this guy is to point to somewhere. All right. Now with this, I can do star A equal 10. All right. There will be some bug here. If you do this right away, the computer will complain. We'll talk about this in a bit. But to use it, I can say star A equal 10. I assign the value 10 into wherever A is pointing. It's a pointer that stores an address. So it's a pointer that keeps the address. Again, it's a data type. it doesn't store a value, it stores an address. The address will point to the location that has this data value 10. So the value of star is an operator. In this case, is the operator that say, hey, get me the value of whatever this guy is pointing at. Because this guy is pointing at the value 10, you get 10 as a result. So you can use ampersand on a variable to get the address, and you can use star on a pointer to get the value. So you can use these two operators to get an address or the value. You can make pointer point to other variable. For example, if you do int b equal 20, and then I say a equal ampersand b. This means that I want a to now point to where b store the value 20. If I use star a afterward, what should I get? Should I get 10 or 20? Now a points to b, so should I get 10 or 20? 20, because a now point to the location that has the value 20 in them.
So the initializing of the variable based on the thing you mentioned at the start for pointer. So if you do it for like letters, you have to do char or
Let me understand your question correctly. Let's say I do char
star A.
Star A, okay.
So it takes address only for the
it basically means that I create the address that points to a character. Now, initialization, that's a great question. Why? Because in the beginning, you get some junk value, which means it point to anywhere randomly, right? So that's why I said, if I do this directly, it will not be viable because I haven't really make it point to a legit location yet. So the way you can do that, you can do it through memory allocation, or you can make it point to some variable that you already declare. Like in this case, B already is declared, then you can use A point to B. You can also increment the pointer. For example, let's say A plus plus, right? So originally A is, let's say 100. If I do A plus plus, because A is an integer, I move to the next item, not the next byte, the next item. So what should be the value of A? 104. Because the next item is at 104. All right. And I can use this, what we call here is what we call pointer arithmetic. It's the operation on the pointer. So how much it go up or down depends on the data type. If the data type is an integer, it go up and down by 4 bytes at a time. Because an integer, one item is 4 bytes. So I want to move to the next item, I go 4 bytes at a time. If it's a character is only 1 byte, so plus plus or plus 1 go to the next byte. So in this case, 100 go to 101. So you want to be careful with the type of the pointer when you do plus plus or minus minus, because it can go up by 1, by 4, or by 8. Now, what about an array? All right, this is where the in-class exercise kind of comes into play as well. When you declare an array, essentially what happened is you create a pointer that covers a certain range. An array of integer with 4 elements is kind of the same as I create a pointer and make a space for 4 items, make it point to that space for 4 items, and you can move up and down. That becomes yours, right? Access to A of 5 is similar to I do this. I go from A, go to the first item, second item, third item, fourth item, the 5th item, then dereference. The star is we call dereference. The name comes from, well, we treat pointer as the reference. The reference gives you the location, right? So dereference means that I have a location, give me the value. So A of 5 is the same as star in parentheses A plus 5. Assuming that you have allocated the memory for A, which we're gonna talk about in a bit. Also, if you have A of 5, right? if you do ampersand on this to get the address, it's the same as just, let's say you have a pointer, in this case, the first locate, like your first slot in your array, and you do a plus 5. This basically means that you can interchangeably use pointer and array. Interchangeably use pointer and array. The big difference is how array is static in size, but for pointer, I can make it point to somewhere else, make a space that are bigger, and make it point to somewhere else, make a space for an even bigger area. All right, so this is one thing I want you to be aware of, right? I can have the integer take value 0, which means it has the actual value of this guy is nothing. But for the pointer, if I want to make sure that the pointer doesn't point to anything, because I mean, let's say I initialize a pointer for the first time, I should not have it point to a random location. That's not safe, right? I can assign it to be null. The null pointer means that it doesn't point to anything yet. And let's say I do int star a, right? I can say a equal null. It means that I force the program to understand that, hey, right now a is not pointing to anything. A is not pointing to anything. This we refer to as a null pointer. In C, you can assign the value null to a pointer. This will force the pointer not to point to any location. And if you try to access the value where that pointer is pointed to, it will generate an error. Each data type has a size, so you can use the size of command. For example, you have the integer, you can use size of int, size of float, or you can do size of the array A. In that case, it's total size for the whole array. In bytes, so you get the data, the return will be in bytes. The store we call this dereferencing. You have a pointer, you dereference the pointer. Ampersand, we call this referencing. You create the reference. Basically, you get the address for that data. So a store ampersand a will cancel each other out. I first get the reference of a, which is the address, then dereference to get the value, which means that it's the same guy. So these are things to be careful. Basically, this is what I want to get at, right? In C, and we do a demo. So today we'll focus more on demo part. So when you use a pointer, please make sure to first, don't forget to declare them. I've seen that before. You forgot to declare them. Make sure it points to a valid location. These are the options. A null variable, an actual variable, or some allocated space that you say, hey, I want to make a space for my pointer. Otherwise, location can be illegal. It can be some illegal location that you're not supposed to access. And the way I think about this, as I said, any data has an address, is the home for the data. If you don't point at the right location, if you walk into someone else's data, it means like as if you're walking to someone else's home. And that's not okay. So what will happen is the OS will kill you, will kill the process. Basically, you run the program has illegal pointer access, that program gets killed. That process gets killed. All right, there's also a special pointer, what we call, I'll call it a file pointer. This points to a file. You can use it to operate on a file, to read or to write to a file. So you can do it this way. A file, something like, for example, file. If I want to use fp as a pointer name, I can do file store fp. fp now becomes a pointer that points to a file. Then I can do fp equal fopen, and then I put the path to the file and the mode. The mode will be read or write. You can read to the file or write to the file. And then afterwards, don't forget to close the file. Don't forget to close the file. You can see how to use it in this link as well. There's additional document for this. And if there's an error, fopen returns null. Fopen returns null. For example, the path doesn't exist. If the path doesn't exist, you get null back. So one safe thing to do is you can do this. If fp equal fopen, this means that if it's a null, which means 0, if you don't do anything in the if you successfully open this, you get non-zero value back because it's a pointer, it's an address, it's non-zero. Then you run whatever in the if clause, meaning that if you can open the file, then do this. If not, or file cannot be accessed or something like that. You can read from a file. So instead of scanf to read from your keyboard input to your terminal, now you can use scanf and put in a file pointer here. For example, like scanf fp %g %a. All right, that will read one integer from a. The same concept applies to get c, get character, get string. So you can use f get c and f get f to open and read a character from a file or read a line from a file. You can write to a file is a printf, which is writing to your screen, to your terminal. You can use fprintf with the file pointer like fprintf fp hello to print hello to a file that you open. And then to tell that hey, that's the end of file, you can use the symbol EOF. That's the end of the file. So to check that, you can call the function FEOF and then the file pointer like FP. This will check if FP is at the end of the file or not. So one thing that's useful is like, for example, while not EOF FP, right? And then read, basically read from FP. These basically allow you to loop and keep reading the file until you are at the end of the file. In general, C use stream to access input and output like file, keyboard, output, keyboard, input. These are in the stream IO. So sample of things in the stream can be file or print to the standard output. Standard output is your terminal. And then you have the fprintf to print to the file and sprintf to print to the stream. All right, so let's take a quick break before we resume and talk about memory. Yes. Yeah. All right, so let's do a quick break for maybe 5 minutes. We'll resume at 12:40. The next thing we have to talk about is memory allocation. Basically, what it means. So when the program begins the execution, right, all your data takes some space. There has to be some room for your data. The program allocates the memory for the variables that you're using, and then it allocates a block of memory for your array. You can also manually allocate the memory for your pointer. You can also manually allocate the memory for your pointer. So when you have a static memory allocation, right, you can do this using an array. For example, you can say int a of 10. These create 10 items, 10 blocks of items for a that I can store integer. And you can use what we call dynamic memory allocation. For example, I need to have a place I can store a bunch of integer, but I don't know the size until I run the program. And then let's say the program have the user feeding in the how many integer do I have to store from 10 to 100 to 1000 or something like that, right? It depends on the size. We can use a function called malloc. Malloc is memory allocation. it basically takes in one input, the size that you want, right? If you want the array for 10 integer, the size should be 10 multiplied by the size of integer. So in that case, we can do 10 multiplied by size of int, right, to get the size for your array of 10 integer. This basically will make the system find a free location in DRAM. Then allocate it, yes.
We know the size of it is 4 bytes, so what we just put that time.
That works too. You can just do 40 in there if you know that you want 40, like 40 bytes. So basically the input is a number. Over here, it's basically become 10 multiplied by 4.
Is that someone to find if the inputs, the input they give, find like what type of like integer, like is it an integer, char or can you find that?
Well, you can do size of char if you want to allocate the 10 slot for your string, right? So you can use size of char. You can just use any number, like you can use 13 in them, like 25, that works too. Basically, what it does is it go find a free space in DRAM with that size. And the return value of malloc is an address that points to the first location, the beginning address of that block. Basically, let's say this is your DRAM, right? And let's just say this is the LAN it find for my malloc. Like I got this. It returned this address. Return the beginning address for that whole block of data. And think of it as a system could find an empty LAN in DRAM and that would fit this exactly this size, then return the address for this LAN to A. All right. So this is basically a little bit more like a animation to show what happened. Let's say I do x equal malloc size of int multiplied by 3. Again, malloc will go find an empty LAN. For example, let's say it's here, right? In this case, let's say the first address is 100, right? Because I do size of int multiplied by 3, it will basically find a space for 12 bytes. And because it's, let's say x is a pointer integer, let's say x is a pointer integer, I can then say star x equal to. If I write star x equal to, what happened? So malloc return what? Is it 100, 104, or 108? Malloc return the beginning address, which is 100, right? If I do star x equal to, means that at the address 100, I put the number 2 in. So becomes this, right? If I do star in parentheses x plus 1 equal 4, x plus 1 move from 100 to what? 104. And I put the number 4 there. If I do star in parentheses x plus 2 equals 8, it means that I now move from 100 to 108 and put the number 8 at that location. This is basically the visualization of what happened when you use malloc and the assignment to the location the pointer is doing. Obviously, as you asked earlier, what if I do x, like I know that x is 100, right? And I force it so that it x points to like 103. In that case, byte 103, 104, 105, and 106 will take, say, 4, which will kind of make this become all junk because you can't really you can recover it back, right? Because it's just a bit of data. But the way you program, most of the time you're not doing that. You're not supposed to do that.
How does it store like a 2-digit number? It's stored into bytes or like into.
Well, 4 bytes is a big area. It stores up to like multiple digits. But let's say it's basically the way it works. Like number 2 is 10 in binary, right? So you would represent this number in 32 bits. So it's going to be 0000010. And that whole thing is put inside address 100 to 103 with that binary.
So you have like the whole byte for the 2 bits.
The whole byte for the 8 bits. Another whole byte for the second part of the 8 bits. Another byte for the third part, yes. Why is original x not a x is a pointer? X is a pointer. Oh, so a pointer can be reassigned. Basically, a pointer has to point to something, right? So and malloc return an address. So in that case, now x point to this location. Originally, it might point to some random location. After you call malloc, it now point to here. And then when you do star x, right? Star x is dereferencing. Dereferencing means that I take x, I dereference, I now look at the block, not the address, and then assign number 2 in that block of 4 bytes. Yeah, the first line will be like in star x.
What would be the result if you take it for the initialization? You put
You mean what would happen if you don't malloc?
When you initialize, it's just the single data x. There's no hash data.
Oh, basically now instead of having address 100, x point to address 2. Yeah, basically it means you change where x point to. So let's say x, you do x equal to, let's say this, you do x equal to, right? It now points here. Which is a totally possible bug you can have in assignment 3. So be mindful about this when you use a pointer. All right, so one sample use of this, like let's say you want to increase the size of your array, right? This will be the in class for next week. We can do this in malloc. And the step is, so let's say you have original array here, right? And this is like a bigger array. So let's say x point here, right? What you do is to create a temp space that is say twice bigger, for example. Then you copy everything over. Then you get rid of this. Then you make sure x now points here. Basically, create a new temporary pointer for your new space. Allocate a bigger size for that temp pointer. Copy everything from the old content to the new content. Deallocate, free up the old content, which we're going to discuss how to do that. Free up the old content. Make sure the old pointer now points to this new temp pointer. Yeah.
In native, so to remove the temporary pointer could be just equal to none.
Oh, well, your question basically is now what do we do with the temp pointer, right? Well, we just keep it there. If the function call finish is gone. Yes. Right. When you do, yeah, exactly. When you do the copy, you do star x y. Let's say y is the new location. You do star y equals star x, then star y in parentheses plus 1 equals star in parentheses x plus 1. Basically, copy item by item. Yes, and then afterward, x equal y to make sure now x point to the same location as y. You free x before you do x equal y. So free is deallocation. Basically, when you no longer need a space, you need to deallocate. If we don't do this, we call it memory leakage. Memory leakage means that the program keep using the memory and never free them. Never free them, keep occupying more and more and more and forget to free. To do this, you mark the region as free. So let's say you have a pointer x, right? You can call the function called free to return the space back to the system that someone else can use it afterwards. Yeah, it's as simple as calling free with the pointer name. You need to do this for assignment 3 to avoid memory leak. Otherwise, let's say you run like 100 applications at the same time and people forgot free, you will run out of memory. Now, the next thing we have to cover is in the memory, there's multiple regions for your data to be on. Some of them is for your code, some of them is for your data, some of them is for like OS specific things. Now, pointer can point to a heap or a stack. Heap and stack are used differently. Stack is the allocation for anything that you have the size known beforehand. For example, you have function call, and inside a function call, you have an array. Right? Inside them, basically, the array will be built on the stack. Essentially, static memory allocation will be done on the stack. Heap is when you allocate new area will be done on the heap. So dynamic memory allocation is done on a heap. So some sample use of pointer, right? Obviously dynamic memory allocation. We can then also implement complex data structure that you guys will learn some of these in the data structure and object-oriented programming. For the purpose of this class, we will learn this thing called linked list. We'll cover this in the next lecture. We might, I'm not gonna put 3 on the exam because you need to take that class first before knowing how to implement that in C. I might implement it for you so that you can see how this is done. We can also use this to pass the array into a function. So now you pass the pointer and the size. But if you have the beginning location and you know the size, you know everything. You can access the whole thing. You can pass data out of the function. So the decode example, for example, the two sum, right? You return a pointer because you have to have the array of size 2. So you can then return the pointer out. This allows you to return more than one thing. You can then pass in a pointer outside from a function. Pointer can also be assigned to a function. We call this function pointer. We will cover this next week as well on Thursday. So function pointer is kind of like a fancy trick that you can then reassign the same pointer into a different function. So you can use it for different purposes. Now, before we jump to the lead code, let's do a sample code quickly. So I'll run two programs. The first program will swap two values using a function call and a pointer. The second program will use a pointer instead of an array. So here, let's go with the swap program. All right. So I write a skeleton code quickly. I have A equals 5, B equals 20, right? Right now, before swapping, I just print A and B. After swapping, again, print A and B. All right, and I call the function called swap. To take the input, what do I do here? What is the input type? A pointer, right? What type? A pointer has a type, int pointer, right? So it's int star A, int star B. You mean?
So like how to do it, like just for initializing integers, you can do int A, comma B, comma C, so on.
It kind of depends on the syntax a little bit. This becomes the integer pointer type A and B for both of them pointer. This pointer A and int B. If I remember correctly, I might not be totally correct with the convention. So if I'm wrong, I'll get back to you. But basically, it depends on like where you put the star. So it's tied to like the thing next to it. Yeah. Usually I just do this much safer. All right, so what do we do? Temp equal what? What are them? Yeah. Yeah. Then star A equals star B, right? And don't forget to assign B back to temp. Any question? Just temp, because temp is just a normal integer. We want to use an integer, but the reason why you pass in the address, right, over here. Okay, let's go with this one now and run it. All right, see the value gets swapped correctly. Now let's do this. Let's just pass in 5 and 20, right? What happened? So quick question, inside the function swap, does A and B actually swap? So inside the function swap, it will happen, right? But is the A and B inside swap the same as A and B in the main function? No, right? The A and B inside the swap is local to A and B. It's a totally new variable. I just passed in the value 5 and 20, so they happen to have 5 and 20, and then you swap them inside.
Use pointers in.
We use the pointer to make sure that instead of passing in the value, you pass the location of A and B. And the location in the main function, the location is the same location. So even though it's a new pointer, it points to the same location, right? So if we do this and run it, you see that it doesn't get swapped because inside the main function, A and B is still 5 and 20. Even though inside the swap function, we swap them is a two different A's and B, right? So that's why we have to pass the address of A and B. So it knows that, hey, that's the A and B that we want to swap. And in here, we need to use the pointer to take the value. All right, so that's a swap function. I'll post the sample code in.
The function, when you write the function, is there nothing like return?
Hmm?
Is there like, you don't have to call like return at the end of the function?
Well, in this case, you don't have to, which is a good observation actually, because I forgot one thing. I said int swap, right? I mean, I don't have to return. I should use void. Void means I'm not returning anything, right? Yes. You can return two things. I mean, if your question is why can't I just return A and B, right? You can, yeah. You mean inside main function or inside the swap? Inside the main, well, you can do that. This is like just to show you, you can use a function call that takes a pointer in, and if I want to return two things, I can do it this way. I would just swap the value, right? All right, the other example, let's say I have array A and B, right? One thing I can do is obviously, I can write a loop. So what's gonna get print here?
What's the point of having B?
Yeah, well, I'll do it afterward. Basically, right now, B do nothing. Yeah, print out 1, 2, 3, 4, 5, right? Basically. All right. Let's see here, 1, 2, 3, 4, 5. Now, if I do this, B equals A, and I do this. Okay, I forgot one more parenthesis here. What will get print? Yeah, the same thing. Why? Because B points to the location of A, right? And you move one item after another. See, the same thing. I add a new line so that we can read easier.
What does the plus C do?
Well, it moved from B plus 0, then B plus 1. So it's the first item, the second item, the third item, the fourth item, the fifth item.
Okay.
Now, let me try something more fun. What if I do this? First of all, will it run? Or will it compile? Okay, let's try. It will give the warning, say, hey, there's a type error, but I can run. It will give something that I'm wrong. Why? Character is 1 byte, right? Basically, right now, I make sure B is a pointer for character. It means that it still can point to a legit address, which means it points to the first location of A. But when I go one position, I don't go 4 bytes at a time. I go 1 byte at a time. So I start from the first byte of A, the second byte of A, and if I keep, let me make it a little bit more interesting. See how the first byte of A is actually like basically I have A have 1, 2, 3, 4, 5, right? But each number is 4 bytes, and the first byte is 1, followed by 0, 0, 0, because the number 1 is a bunch of zeros and then 1. So the first byte B is pointing is that number 1 followed by 3 more zeros, right? And it happened to be the same for all this. Now, let me change something more. So you know that 255 is like basically 1 byte long, right? And if I do 256, it's 1 more byte. If the first number is 256, this is 1 and then 80. 1 and then 80. If I compile this and then print it out, see how 1 and 80. Now the first byte, 1 byte is 8 bits, right? So the first 80 becomes 0. Because the number is 256, the ninth bit is 1. So it go read that byte and it's like, oh, it's 1. Then it read the next byte, 0. I can also do this, play around with the bits, right? Now the first byte is all ones. Now all ones in binary is -1. If I want to make it more clear, I just do unsigned, actually. Unsigned means that I don't have a negative number. It goes from 0 to 255. You see that the first byte is then 255, because we do 255 plus 256. So it's going to be 1, 1, 1, 1, 1, 1, 1. 1, 1. Sorry, it's 9 ones. The first set of block of 8 ones is the first byte, so that's 255. Then you have 1 more number 1 in there in binary. Yeah, we can do that as well. So let's change this to short. One thing I have to change is now it should be go up to 10, otherwise I go over the array size. Here, right? Because it's short, we read 2 bytes at a time. 2 bytes, the first 2 bytes is 255 plus 256, that's 511. So that's why it print 511, 0, 2, 0, 3, 0, 4, 0, 5, 0. No, basically it flow into the, well, right now the number is 2 bytes long, right? But your original array is an integer array, so it's actually 4 bytes long. So it means that if I have the number bigger than 256, for example, right? It's a character pointer. It only will modify that only 2 byte chunk because it knows that, hey, this thing not supposed to like overflow into the next byte. So it will do the addition, and then it will only crop out the first 2 bytes and assign them. The whatever remains, we throw it away. Yeah, but great question. All right, so many things from this example. First of all, if you have a mismatch type, one quick thing, the compiler will yell at you, say, warning, this looks wrong, right? So when you have a warning, please check because some of them are legit warning. Some of them, if you know what you're doing, it's okay. All right, but most of the time, I would try to get rid of the warning because most of the time it bugs somewhere on your code or something not too safe.
What will happen if you just do unsigned? You just keep it unsigned where it's 256. There's no addition.
What do you mean?
You just keep it 256 as a first array element. You need to remove the 255 plus.
Oh yeah, sure. Here, right?
So what would happen?
It should be 256 in the beginning because 256 is within 2 bytes. So I print that out.
What if there's no short?
Huh?
If there is no short, it's just unsigned.
Unsigned what? I mean, you have to assign a data type, right? You can do unsigned char. Here it will be 0, 1. Instead of 1, 0, it becomes 0, 1 because the number 1 moved to the 9th bit. That's the second byte. Basically, let's look at the first 2 bytes, right? The first byte becomes this 8, 8, 0. So that's the first byte. Right? This is number 256. Right? This is exactly 256 in binary, right? Because we move from just 1, so the character, the first byte is this guy. So it print out 0. Then it print out 1, right? Because the next byte is of 256. It's 0, 0, 0, 0, 1. Then afterward, it's just another like bunch of 0 and then another bunch of 0, right? So that's why I print 2 more 0. And then the next byte, that's when we go to the next element in your array. So in array A, it's 1, 2, 3, 4, 5, right? But instead of 1, we have 256. So it's 256, 2, 3, 4, 5. So the number 2 is basically, right? This is number 2. Then you see a bunch of 0 again, right? And so on and so forth.
So short basically combines them.
Short, basically when I have short is an integer, but only not 4 bytes integer, 2 bytes integer.
So it does the calculation 4 bytes.
It points to the address and it only takes 2 byte range. Yeah.
the value will change for the number if it's like beyond 2 bytes.
Uh,
Or this case, like, let's say 256 plus 256 plus 256, that'll come in like 3 bytes.
what do you mean? I'm a little bit confused now.
There are 4 bytes here.
In this one number,
Yeah.
yes. Uh-huh.
And if the short makes it so it only takes 2 of them,
Yes.
you overflow one of them.
Oh, but for the short, if it's overflow, basically it's the same as this question, which is I only crop the first 2 bytes. I don't care about the rest. Now, let me play one more weird thing for you, right? So we don't loop. Let's assume we don't loop around. I want to print just one number. I want to print just one number. And let's say I do B star B equal A, right? And it's unsigned char. Oh, and then actually, here's what I do. I want to print the array. I want to print the array out, so it's just A of C, right? This, if I do nothing here, it should print 1, 2, 3, 4, 5. All right, everyone agree with me? Okay. Now, what if I do this? So I go at the beginning of A, but I don't modify the first byte. I modify the third byte and set that to 1. So this is what's gonna happen, right? The beginning of A basically is 4 bytes long, number 1. So it's gonna be 0. So that's A. That's A. All right. That's the first byte. So that's star B. That's where B is at. This is where B plus 1 is at. Here. This byte is where B plus 1 is at. All right. This is where B plus 2 is at. Okay, with me so far. I changed this to 1. Yeah, it actually convert this to decimal, basically. Yeah. So there should be, wait, what should this be? Someone help. 16, 17 bits, 16 bits, 2 to the 16, that's 180,000 something plus 1. 128,000 something plus 1. Something around that range. Here. Oh, actually a lot more. Sorry about that. But yeah, you see that it becomes that number. Let's confirm this. Okay. Sorry about that. Okay. All right, 65537. All right, 65537. Because what we just did is we modified the third byte in A into 1 because of my code here. If I do, instead I do this, then I basically do this instead, right? So what if I do this? What will it print? If I do star B plus 4 equals 1. Star B plus 4 now move to the second item of A, right? Because B plus 4 is we move 4 bytes. We move out from the first item, so number 1 will remain intact. The second item of A used to be number 2. Now we change number 2 to be number 1 because that first byte from 2 we now change to 1. So the second item of B used to be like this, right? It is number 2 in integer. And we are currently pointing at this byte and say make that 1. Because my pointer is an unsigned chart, make that 1, make that whole thing 1 instead of 2. So what will happen from this line if you run it is this. So you should get 1, 1, 3, 4, 5. See? All right, let's try one more thing. What if we try to access something that you're not supposed to access? You don't have that for sure, right? Let's run. It will tell you segmentation fault. Segmentation fault is the features from your OS that say, hey, if this program looks dangerous, kill it. Why? Because that location doesn't belong to you, right? In the yes.
What would happen if you same thing that happened to go and then
Different. This is basically the mechanism for OS to protect someone else's program that are running. Because you never know where that location is. It might be someone else's code, it might be someone else's data, right? So this basically means that, hey, that's not yours. That looks sketchy. Let me kill you. Yeah. And it's a good thing because if you happen to modify that and just happen that part is like something owned by the kernel, it might crash your computer, right? Yeah. So when you see segmentation fault, right? We'll talk a lot more next week when we talk about the tools called GDB. It's a debugger that allows you to run code line by line by line. This semester, I'll make sure that I go over GDB in more detail because most of the time you're not using it for this semester, but you will see that and how powerful it is in the PCSA class, which is the class after this course. All right, so basically for the remainder of today's lecture slot, like for the next 30 minutes, try out the two lead code problem. You should be finished them.